Hey guys, welcome to my channel. My name is Piyush Wadhawan and in this video I'm gonna talk about the evolution of processors. The topics that I'm gonna cover are what is a processor, its basic definition along with its function, moving to the invention of processor and how the processors are made. In this we'll study the in-depth method of processor manufacturing, moving to the generation of processors, the classification of processors over the years and finally the evolution of processors. So what exactly is a processor? A processor is basically a tiny chip that's embedded in most of the electronic devices that you're using nowadays. Now, I don't just mean your laptops and computers, it can also be a mobile or a radio. The function of a processor is to receive a basic input and provide a appropriate output for that. Now, as an example, you can take your basic mouse or a keyboard input and you see some output on your screen. That's basically due to the processor. Some other examples can be handling basic arithmetic calculations to handling trillions of calculations per second. CPU, your central processor of a computer or central processing unit, handles all the basic instructions and running of applications. Most desktop computers contain CPU that's developed either by Intel or AMD. Some companies that develop your mobile processors are ARM and Apple, but in nowadays modern CPUs are often including multiple processing cores, which I will explain in the next slide. Now, multiple processing cores. What exactly does this mean? So let's just take a square and assume that this square is a processor. This is connected to a socket. Now let's take three processors. So each of these squares represents a processor. Let's name them as 1, 2 and 3. So what multiple processing cores means is that there are multiple individual processors, that is 1, 2 and 3. They are individual processors and they are connected to the same socket. This basically means that their ability to connect with each other is faster and so they work faster in return. So equivalent, they work faster. That's basically it. Now this diagram is just for your understanding. Don't assume that in a real circuit it's really like three microprocessors just connected with a single wire to a single point. That's not it. This is just a diagrammatic representation for your explanation. The invention of microprocessors. So the very first microprocessor was developed by Intel in the year 1971 in the month of November. The name of the first microprocessor was Intel 4004. It was developed by Ted Hoff, Federico Fagin and Stan Maser. You can see the image of the microprocessor on the right hand side of your screen. Now I will discuss this in detail in later slides, so I will move to the next topic. Now, how are processors made? A processor consists of a base that's called a wafer upon which the rest of the processor is built. So that base is made from silicon, which is a semiconductor. So the material you dope it with will determine its electrical properties. So we take some silicon and put it in a quartz vessel and heat it along with some phosphorus and antimony to form a melt. Now after it reaches a certain temperature, we slowly lower an ingot into the melt and cool it. As the melt is cooled, crystallization begins to happen on the surface of ingot. Now what this ingot actually is, it is just a cylindrical circular deposit that's lowered into it upon which crystallization takes place. Now after it's cooled and the ingot is slowly taken out, rotating it. The rotation is done so that any temperature irregularities can be corrected, and it's basically bullet shaped, right? So the ends of the bullets are cut off as they are the most impure part of the ingot, and so we get a pure cylinder. Now cylinder is basically circles stacked upon each other. So we take the ingot and cut circles using some fine sharp saw blades, and they're cut in circles to avoid any chipping or cracks in them. This is basically how the wafer is made, and if you want you can add another layer on it of coating. That's basically a wafer. Moving on. Okay, so after a wafer is made, we go through something called etching. Now, etching is done in order to create some gaps or in order to create some cavities onto the wafer. It's like creating a pattern. So basically, these are the processes involved in etching. The first process is the implanting of an oxide. So basically, the wafer is covered with an oxide. This is mostly done by exposing the wafer to steam at very high temperatures. After this comes the photoresist, in which an organic material is applied onto the wafer. This acts like a film in a camera. Now, that organic material is called a photoresist. And after that, masking is done where a mask is applied. Now that mask doesn't fully cover the wafer. It has gaps in it. And through those gaps, UV light is shown. UV light is used because it has a shorter wavelength, and a shorter wavelength basically means that it can pass through smaller masks. So the UV light hardens the photoresist in certain areas where the gaps are there. Cleaning is basically the removal of the unhardened mask, which wasn't in the gaps. So that is basically removed with an organic solvent, after which the main process etching comes, in which an hydrofluoric acid is used to etch away the silicon oxide. Since hydrofluoric acid is an inorganic, it does not really attack the photoresist. So the cleaning of the photoresist is the last step, which is basically to remove the photoresist that was remaining on the wafer, and now that wafer is ready for doping with another type of silicon or for adding contacts. So after the process of etching is done, we move on to making of a transistor. In this, a p-type wafer, that is a silicon doped with boron, which has an epi layer of n-type, that is silicon doped with phosphorus and arsenic. A mask is then used to implant silicon dioxide for the insulator. Acceptor atoms, that is boron, are diffused into the window in the silicon dioxide. After this, we use another mask. Additional silicon dioxide is grown, and donor atoms, elements like arsenic and excess electrons, are implanted on it. Another mask is used to grow additional silicon, and another mask is then used to implant evaporated aluminium or copper for the contacts. This is basically your bipolar junction transistor, and this is what is embedded inside your electronic devices. So this is the end of the manufacturing process of a microprocessor. Okay, so the generation of microprocessors. Now the microprocessors have been classified across 5 generations. The very first generation ranges from the year 1971 to 1973, and this generation is regarded as the very first generation of microprocessors because it is during the year 1971 that Intel created the very first microprocessor, Intel 4004, and this ran at a clock speed of 740 kilohertz. Other processors were also existing as well, but these were not in use as they were not TTL compatible. And what TTL means is the transistor logic. Moving on to now the second generation of microprocessors. This generation ranges from the year 1973 to the year 1978 and is regarded as the second generation. This was a leap from the 4-bit microprocessors to the 8-bit microprocessors. Some examples are Motorola 6800 and 6801, Intel 8085 and Zilog's Z80, which were among the most popular ones. These microprocessors had faster speed than the first generation ones, and they were costlier as they were based on the NMOS technology fabrication. NMOS stands for negative channel metal oxide semiconductor. Basically, it is a type of semiconductor that charges negatively. Moving on to the third generation of microprocessors. During this period, the 16-bit microprocessors were created. This period ranges from 1979 to 1980. Some common examples are Intel 8086, 80186, 80286, Motorola 68000 and 68010 were developed. Speeds of these processors were 4 times better than the second generation processors and were obviously faster than the first generation processors. The third generation was again a departure from the 8-bit microprocessors to the 16-bit microprocessors, and they use HMOS technology, which is high performance and channel metal oxide semiconductors, basically a chip with a high density of NMOS transistors. Moving on to the fourth generation, which ranges from the year 1981 to 1995. This generation was again a departure from the 16-bit to the 32-bit microprocessor by using HCMOS fabrication. HCMOS stands for complementary metal oxide semiconductors. Some common examples are Intel 80386 and Motorola 68020, 68030. These were the popular ones in this era. Now, fifth generation of microprocessors, which ranges from 1995 to the current year, and it has been bringing out high performance and high speed processors that make use of 64-bit processors. Such a processor include Pentium, Celeron dual quad-core processors. So this is basically the generation of processors. Moving on to the next topic. So our last topic for today, that is the evolution of processors. Now in this topic, I'm not gonna talk about every single processor that has been made till now. I'm only gonna talk about some specific processors that have been developed by Intel that actually had a major impact on the history of microprocessing evolution. So the very first one I've taken is the Intel 4004. Now, this was the very first processor that was made by Intel. It had a 4-bit and was developed in 1971 with a clock speed of 740 kilohertz. Now, what a clock speed means is it's basically the number of clock cycles that it can run per second. Basically, it is the speed. And the number of transistors that it had was 2300. You can see the image on the right hand side. Moving on, we have Intel 8008, the next one in the list, which is a transition from the 4-bit to the 8-bit. This was the first 8-bit processor and it was actually a replacement for the Intel 4004. It was made in 1972. It has a clock speed of 500 kilohertz, and this processor laid the foundation for Intel 8080, 8085, 8086 processors. Moving on to the next one, which is the Intel 8080. This is again an 8-bit processor and it was developed in 1974 with a clock speed of 2 kilohertz, and the number of transistors that it had was 60,000. This processor had a speed that was 10 times the speed of the Intel 8008. Now it was faster than the Intel 4004 as well as the 8008. Moving on to the next one, we see Intel 8086. Now this was again a transition from the 8-bit to a 16-bit processor. This was the very first 16-bit processor that was created by Intel. It was developed in the year 1978 with a clock speed of 4.77 megahertz. Number of transistors was 29,000. It laid the foundation for the Intel 8088. Now moving on to the Intel 8088. This is a 16-bit processor again, developed in 1979. This was a cheaper version of the 8086. So the most prominent difference between the both is basically the price. The Intel 8088 was a much cheaper version, and because of that it became a more productive one than the previous. So moving on to the next one, we have Intel 8386. This is a 32-bit, the first 32-bit transistor that was made by Intel, developed in the year 1986, clock speed 16 megahertz and number of transistors 275,000. Moving on to the Intel Pentium. This is a 64-bit processor. This is again a transition from the 32-bit to the 64-bit processor. This was faster and it was much convenient to use as it didn't get heated up as much as the previous ones. Developed in the year 1993 with a clock speed of 66 megahertz. Moving on, we have the Intel Core 2. This was developed in 2006, again a 64-bit processor, clock speed 1.2 to 3 gigahertz. Number of transistors 291 million. Now we have some more processors in the next slide. Let's see them. And we have the i3, i5 and i7, which are basically the upgraded versions of each other. And I think that's it for this video, guys. I hope you enjoyed and thank you for watching the video.